Welcome to The Explainer. We've all been there, right? You're using an app and it just feels slow. It's frustrating. So today, we're going to peel back the layers on that feeling. We're going to build a real intuition for why systems slow down under pressure and dig into the big choices we have to make when we design for growth. So here's our game plan. First, we're going to take that vague idea of slowness and turn it into something we can actually measure. Then we'll go on a hunt for bottlenecks, pop the hood on our systems engine, and finally, look at the two big strategies for handling massive scale. All right, let's jump in. Okay, so let's get right into it. When a user says your app is slow, what are they really talking about? It's a feeling, a gut reaction. But see, in engineering, we can't really fix a feeling. We have to translate that frustration into a cold, hard number, something we can measure, track, and actually improve. It always starts with just one click. A tap on a screen. But that one tiny action, it's like firing the starting pistol for a marathon. A request gets fired off across the internet, it has to navigate through all your servers and databases, and then it has to make that entire trip back before anything even starts to happen on the user's screen. And this really breaks that whole journey down. As you can see, slowness isn't just one single thing. It could be the network having a bad day, a server that's totally slammed, a really tough database query. Seriously, any one of these steps can add milliseconds, and those milliseconds are what add up to that frustrating wait the user feels. And that total time for that entire round trip is what we call latency. This is it. This is the fundamental concept. When a user says slow, they are talking about high latency. It's the one metric that perfectly maps to how a person actually perceives your system's performance. But here's the trap that so many people fall into. See, latency isn't just one number. You might have 99 requests that are lightning fast, but then one that's just painfully slow. And if you just average them all out, that one person's terrible experience gets completely washed out by the math. This is exactly the problem I'm talking about. Your dashboard might show an average latency of, say, 200 milliseconds, and you're thinking, hey, that looks great. But what that average is hiding is the 1% of users who are staring at a loading spinner for 5, 10, maybe even 15 seconds. The average makes you feel good, but the percentiles, well, that tells you the real story about your most frustrated users. And this is exactly why the pros focus on high percentiles, like the P99. It tells you the experience of your absolute unhappiest 1%. And think about it. Who is that 1%? It's probably not someone just loading the homepage. No, it's your power user running a massive report or a huge customer checking out with a giant cart. These aren't just outliers. They're often your most important transactions. Okay, so now we know how to measure the speed of a single request. That's latency. But that's only one piece of the puzzle. The other piece is capacity. This is where throughput comes in. Throughput measures how many requests your system can juggle at the same time. Because, hey, low latency for one user is great. But what happens when 1,000 of them show up all at once? Now, this is where it gets really interesting. As your throughput starts to climb, your latency doesn't just go up in a nice, neat, straight line. Nope. It stays pretty low for a while, and then, all of a sudden, it hits this tipping point and just skyrockets. So why does that happen? The reason is one super important concept called utilization. And to understand it, let's just think about an ice cream shop. So to get a handle on utilization, just picture an empty ice cream shop. You walk in, you're the only one there, you get served right away, your request is handled instantly because the worker, your server, is totally idle. That's low utilization, and your latency is amazing. Okay, now picture that exact same shop on a hot day, right at lunchtime. There's a huge line out the door. Now the person behind the counter is working at the exact same speed, but it doesn't matter, right? Because you have to wait in a queue. Your personal wait time, your latency, has gone through the roof. That is the effect of high utilization on a server. And this right here is the key takeaway for any bottleneck hunt. Your gut feeling is probably wrong. It's so easy to blame the big obvious thing, like the database. But a lot of the time, the real culprit is some small, forgotten bit of code, like a logging service that's secretly holding up the whole process. The only way you're going to find it is to follow the data. The rule is measure, don't guess. Period. All right, so speaking of the database, it often is doing the heaviest lifting, so it's actually a great place to start looking for performance wins. Let's go over a few of the most common problems engineers find and fix in the database all the time. First up, the notorious N+1 query problem. Okay, imagine you need to show 100 blog posts, and each one needs the author's name next to it. So you make one query to get the posts, great. But then you start to loop through those 100 posts, and for every single one, you make a separate trip back to the database to get the author. That's 1 plus 100, 101 round trips to your database. The fix for this is almost laughably simple. You just ask for everything you need all at once. One query for the posts, and then one single query to get all 100 authors together. You go from 101 trips to the database all the way down to just 2. This is often the single biggest, easiest performance gain you can make. Next up are indexes. Think of a giant library, but with no card catalog, no computer search, nothing. To find one book, you'd have to literally walk down every single aisle and look at every single shelf. That's what a full table scan is in the database world, and it's incredibly slow. An index is that card catalog. It tells the database exactly where to go to find the data it needs. And finally, there's the actual cost of just talking to the database. Opening a brand new connection for every single request is like having to dial a phone number, wait for the person to pick up, say hello, and confirm who you are, just to ask one quick question, then hanging up. It's wildly inefficient. Connection pooling is like keeping an open line to a whole bunch of operators who are just waiting to take your call. It saves you all that setup time for every single request. Okay, so you've tuned your queries, you've added your indexes, you've set up connection pooling, but under a really heavy load, your database is still the bottleneck. So what's next? Well, the next layer of defense is caching. This is where we store the results of expensive work in a much, much faster layer of memory. There's this famous quote in computer science that says the only two hard things are cache invalidation and naming things. And it's so true. The idea of caching is simple. Save a result so you don't have to do the hard work again. But the challenge is huge. What happens when the original data changes? You have to make sure your cache copy gets thrown out. This is cache invalidation, and it's notoriously tricky to get right. The way we measure how well our cache is working is with a metric called the cache hit ratio. It's super simple. What percentage of requests got their answer from the super fast cache, that's a hit, versus the ones that had to make the slow trip all the way back to the database, a miss. A high hit ratio means your cache is doing its job and saving your system a ton of work. Okay, so our system is now fully optimized, but we know we're going to get more traffic in the future. So we hit this fundamental fork in the road. How do we prepare for that growth? Do we build one single, bigger, more powerful machine, or do we build an entire army of smaller ones? And these are the two paths you can take. Vertical scaling, or scaling up, is like trading in your car for a massive semi-truck. It can carry way more stuff, and it's pretty simple to manage because it's still just one vehicle. But there's a limit to how big a truck you can build, and if it breaks down, your entire delivery system is offline. Now, horizontal scaling, or scaling out, is totally different. It's like buying 1,000 delivery vans instead. No single van is all that powerful, but together they can handle almost infinite load. And if one van breaks down, the other 999 just pick up the slack. It's incredibly resilient, but it's way more complex to coordinate. And really, that's what all of this comes down to. Performance engineering isn't just about making things fast for the traffic you have today. It's about designing systems that are resilient, systems that can gracefully handle the pressure of tomorrow. So the question I want you to take away from all this and ask of your own systems is this: when the pressure inevitably comes, is it built to bend or is it built to break?